Welcome to Module 2 of our machine learning journey, where you'll be mastering the art of exploratory data analysis. Remember, learning is a collaborative experience. Feel free to ask questions in the comment section below and engage with fellow learners. You can revisit any key machine learning concepts in Module 1 at any time if needed. But EDA is a powerful tool that goes beyond machine learning. It helps researchers formulate hypotheses and enhance data-driven decision making. The Sydney Informatics Hub is a core research facility supporting computational and data-driven research. But at the heart of it all, we are a facility built on people with diverse expertise in data science, computing, and beyond. We offer access to research infrastructure, such as high-performance computing, project and grant support through flexible consultations, and events such as hacky hours, seminars, and training workshops, just like this one. Our areas of expertise span across 4 key domains: statistics, data science and software engineering, research computing, and bioinformatics. This may include shaping robust experiments and harnessing AI as predictive tools to large-scale modeling and custom omics pipelines. To engage with us, you can reach out directly through our Contact Us button on our website or scan the QR code and fill out our request form. You can also send us an email and we'll promptly be in touch. This is the second of 4 modules in our exciting new machine learning workshop series. If you haven't seen it already, please go check out our video on Module 1. Please remember to register in Eventbrite for Modules 3 and 4, where you'll be getting hands-on experience with building models and turning them into predictive tools for research. As I'm sure you're all familiar, after gathering data, the focus turns to exploration. This phase helps to refine research direction, validate assumptions, and assure analysis reliability. Even if your sampling methods are planned carefully, real-world factors can lead to unexpected variations across sites, batches, people handling the samples, or just naturally within the environment. Plus, a lot of the time, data is often recorded for convenience, which might introduce human error. So it's not exactly surprising when researchers invest a significant portion of their time trying to clean and organize their data. It's not just a routine task, rather it serves as a crucial quality check and forms the foundation upon which successful research outcomes are built. Before diving into machine learning, you start with exploratory data analysis. This helps you build a mental model of the data, validating the accuracy of your predictions. And some key questions to ask yourself during this process include: what question are you trying to solve or prove wrong? Start with the simplest hypothesis, then add complexity as needed. What kind of data do you have? Is it numerical, categorical, or something else? How do you deal with each type? What's missing from the data? Why is it missing? How do you handle missingness? Where are the outliers? Pay attention to distribution. Do you need them, or are they damaging the model? How can you manipulate features to get more out of your data? Although more data can be good, sometimes simple is best. So start with minimal but impactful features to maximize insights. And within the machine learning context, getting your head around these things will allow you to make more informed decisions about data pre-processing, feature engineering, and outlier handling before you build your models. So let's go through each step together using an example dataset. This dataset is a compilation of passenger information from the Titanic downloaded from Categorical, which is a platform where people can explore, learn, and compete in data science and machine learning challenges. And this dataset typically includes information such as passengers' age, sex, ticket classes, cabin locations, and whether they survived the disaster or not. And the question we're trying to solve is, can we predict survivors on the Titanic based on data from other passengers? And a quick look at the data reveals an assortment of columns. So you have numeric, there's text, and there's a mix of both with some NaNs sprinkled in. So let's make this simpler. By dividing these features into numerical, categorical, or not sure, allows for a more organized approach to understand and processing the data. Because survival is the feature we're trying to predict, we'll take it out of the numerical bucket and leave it for the time being. So EDA doesn't always require code. You can use your understanding of the subject and check its accuracy later with code. So another feature we can probably put aside is passenger ID, as it's unlikely to help predict survival. But what about these 3? Looking at the data dictionary, we can see that they correspond to ticket class, the number of siblings and spouses, and the number of parents and children aboard the Titanic. All of them sound like they could be useful, so we'll keep them in the model. Now, This information is pretty easy to find online because it's a publicly available dataset. But imagine facing unfamiliar columns in a different dataset. So when that happens, you might need to ask for clarification from the client or do more research. Now, focusing on the categorical bucket, these are features that represent distinct groups or categories, which can be divided into nominal or ordinal types. Nominal variables represent categories with no intrinsic order, so these can't be ranked, whereas ordinal variables can, because they have a hierarchy. And both of our features are nominal. We can separate passengers who are female from those who are male, or those who embarked from Cherbourg, Queenstown, or Southampton. To train a machine learning model, we need a way of converting these into numbers. One-hot encoding is typically applied to nominal categorical variables. This process converts each category into a binary column, indicating its presence, 1, or absence, as 0. This way, it avoids implying any ordinal relationship between the categories. For ordinal variables, we would instead use integer encoding or other techniques that preserve their ranking. In the remaining bucket, we are left with 3 features: name, ticket, and cabin. Cabin sounds like it would be relevant, whereas it's unlikely that name will directly impact survival chances. Likewise for ticket, it might not provide significant insights, especially since we already have class information in P-class. Thus, for simplicity, we'll also set aside ticket. Remember, one of the primary goals of EDA is to start with a basic model with minimal but impactful features to maximize insights. You can always add more later. The next question I'm going to ask is, what is missing from the data? How can you make predictions when information such as age or cabin are absent? It's definitely a challenge. Removing rows with missing values might seem like a quick and easy solution, but you're also losing large amounts of data, which will likely weaken our model's predictive power. Imputing values, so filling missing data with calculated values, is another option. For instance, with the age column, you could use the average age. However, this approach has drawbacks. If many ages are missing, it skews the data towards the average, therefore affecting predictions for various age groups. Another option is finding similar people with known ages, but it's time-consuming. So, although imputing values keeps more data, it can potentially introduce bias. So, various methods exist for handling missing data, but no approach is perfect. Balancing between data loss and data quality is essential, as it directly influences our model's effectiveness in making accurate predictions. Speaking about quality, what about outliers? Outliers are data points that significantly deviate from the typical pattern dataset. They are unusually high or low values that can skew statistical analyses and models. As a general rule of thumb, you may consider anything more than 3 standard deviations away from the mean to be a potential outlier, but the definition of an outlier will vary between datasets, which is why identifying them is crucial, as they may be errors or valuable insights. And you can find them by looking at feature distribution in your dataset. For example, on the right is a histogram of age in the Titanic dataset. Do you see any outliers? Would you remove any age values or keep them all? More importantly, why should you care? Removing outliers is important because they can distort the results of your analysis or the performance of your models. In machine learning, including outliers can lead to models being overly sensitive to these extreme values rather than capturing the underlying patterns of the majority of the data, resulting in poor generalization to new data. So handling them appropriately is essential to ensure reliable and meaningful results. The Titanic dataset only has 10 features, and it started out in pretty good shape. We've already transformed some features and dropped others. But what if your dataset has hundreds of features or thousands more? That isn't uncommon. So this is where feature contribution comes into play. For instance, using our Titanic example, we can see that sex in class had the highest contribution to predicting survival. Think, save the women and children. This information guides your feature engineering decisions. Have you had hundreds more features? You could create a graph illustrating the contribution of all features. This insight will then enable you to prioritize and refine your feature selection. The rationale for focusing on high contributing factors is twofold. First, removing less influential features reduces the complexity of your data, streamlining your model's decision-making process. Second, the streamlined model might achieve comparable or even better results using less data and in less time. EDA and model building is a continuous and iterative process. Cycle begins with EDA after you collect your data, and during the EDA, you analyze and visualize data to gain insights, identify patterns, and understand relationships between features. Now, these insights help you make informed decisions about data pre-processing, feature engineering, and outlier handling before building and fine-tuning your model. After which you loop back to EDA, reevaluate the model's performance, investigate any anomalies, and assess whether your assumptions still hold true. This might lead to further refinement of your data, features, or model architecture as you improve its accuracy and generalization ability. As you can see, it's a really dynamic process that empowers researchers to create strong, robust models, ultimately accumulating in research outcomes that are more reliable and have greater impact. As we wrap up, your feedback is invaluable to us. Please take a moment to scan the QR code and share your thoughts. We sincerely appreciate your engagement and encourage you to explore additional information via the provided links. Don't forget to show your support by hitting like and subscribe.